Hello, my name is Yash Chitalia. I am going to talk about the design, modeling and control of a microscale, multi-degree of freedom robotic guidewire. Clinicians often manually navigate a thin flexible wire known as a guidewire through tortuous vasculature during procedures for peripheral artery disease. In this work, we propose the design of a novel steerable guidewire tip with 2 degrees of freedom motion capability. This robotic guidewire has a diameter of 0.78 millimeters, making it well within the range of diameters used in medical grade guidewires. This tip is manufactured by etching asymmetric notches in a nitinol tube and passing tendons through the inner lumen as seen in the bottom left image. Each joint is controlled by 2 tendons. We perform a kinematic analysis of the robot, assuming that each joint deforms with a constant curvature. Attaching frames to the base and tip of each joint, we can compute the workspace of the robot shown to the top right. However, for inverse kinematics, we iterate over each joint numerically to find a solution for the joint curvatures. Getting actuator displacement is difficult for such small sizes because geometric solution is not enough. Joint statics and friction effects contribute heavily towards the robot-dependent kinematics, thereby making this relationship non-trivial. This static relationship is approximated by a linear bending model. Each joint is composed of several notches, each of which is assumed to be made up of 2 cylinders connected by a curved wall. Furthermore, tendon routing adds friction losses to the static relationship. We assume a Coulomb friction model for the same. We create a setup with varying wrapping angles and measure hysteresis for each wrapping angle as seen in the image. This allows us to account for friction effects and approximate the bending stiffness of the joint in the absence of friction. Similarly, the coupling seen due to tendon routing between joints seen to the bottom right is also modeled. The observer block shown in the control system to the top left uses observed tendon tension and the static and friction models discussed previously to estimate the shape of the robot in joint space. Then a joint space PI controller is used to send commands to the actuators. Figures A and B seen in the center of the slide show tool tip tracking performance for various trajectories. The video shows plots of the PI controller for the base joint following several tooltip trajectories in Cartesian space. To the bottom right is a preliminary performance taking the coupling model discussed previously into account. Thank you, and please visit our poster for additional information.